Let's review what we have been studying with regard to Mohr-Coulomb criterion. Please note that we say that normal stress is plotted against shear stress, and if you plot, you can fit the data and fit a straight line. Mohr-Coulomb first started with simply normal and shear stresses, so the equation of this failure envelope will become the shear stress is equal to the intercept C plus some normal stress and tan phi. Phi is nothing but the slope of this line. Look at the angle made by the failure line, which means as you increase the shear stresses, the shearing stress, it can raise and reach up to this point. There is no state possible, and that is why we call it as an envelope. Please remember, this is what Coulomb originally started, and then what Mohr said was, instead of looking at normal and shear stresses, he said let us plot the maximum principal stress sigma 1 and the minimum principal stress sigma 3, and you will get the circle. And what he said was the failure envelope is tangential to the Mohr circle. So again you will get an intercept here and the angle here, and that angle again of course is angle of shearing resistance. You can also plot in terms of the average stress sigma 1 plus sigma 3. See, the center of the Mohr circle is here, so the intercept from origin is sigma 1 plus sigma 3. This intercept is C and this angle is phi, so you get C cot phi. So you can then say this is C cot phi plus sigma 1 plus sigma 3 will give me the distance from this point to the center of the Mohr circle, and you will find the radius is equal to half the difference between the two principal stresses. So sigma r is equal to sigma 1 minus sigma 3 by 2. And you can see that these can be related. Sigma 1 minus sigma 3 by 2 by this is nothing but sine phi. So I can even say Q is equal to C cot phi plus P into sine phi. This is another way of looking at the failure envelope. The other interesting thing you find is the envelope is touching the Mohr circle at this point. If I draw this point line, it makes an angle of 45 plus 5 by 2. Or from your simple trigonometry, you can say that this is twice that. So this is pi by 2 plus phi. So the failure envelope is inclined at 45 plus 5 by 2 to the major principal stress. So you will find that the state of stress defines the failure envelope. Here is the mechanism for direct shear test. You have two boxes filled with soil. You apply a normal load and you apply a shear load. So normal force divided by cross-sectional area gives me the normal stress, and if I divide the shear force by the area, I get the shear stress. The only thing complicated here is that you are forcing the failure through a horizontal plane. So there is a shear stress and a normal stress, which means the principal stresses are not along this direction, they are oriented in some direction, and unfortunately we will not be able to determine this orientation. What is the angle between, for example, the vertical and the major principal stress, or the horizontal and the minor principal stress? But if you are just using Coulomb law, a direct shear test is good enough for us. In the triaxial test, as I said, you can now apply sigma 1 and sigma 3, and this is the angle of the failure plane, which makes 45 plus phi by 2. So you know the failure plane, you know the Mohr-Coulomb failure envelope. I am doing the test at 3 confining pressures, sigma 3 1, sigma 3 2, and sigma 3 3. And you draw the Mohr circles 1, 2, and 3. If I draw, I get the shear envelope, failure envelope. And the intercept here is called cohesion, and the slope is called angle of shearing resistance. If C is 0, it becomes a purely frictional material. The strength depends only on angle of shearing resistance, and there is no cohesion intercept. So you draw the Mohr circles here and draw a line you will get C and phi. This is how we try to determine C and phi. A tangent to all the Mohr circle. You can also draw in terms of mean principal stresses. P is equal to sigma 1 plus sigma 3 by 2 and Q is equal to sigma 1 minus sigma 3 by 2. Again, if I fit a line, I can say Q is equal to C cos phi plus P sin, which means this intercept D is nothing but C cos phi, and you will find that the slope of this line psi tan C is equal to sin phi. As you can see from this relation, we derived that Q is equal to, all that you have said is C cos phi, that is this intercept, and P sin phi. So you can plot PQ and fit a straight line, and the intercept gives me C cos phi plus average principal stress into sin phi. In case of both compacted soils, even in sands, at low confining pressures, you get a very high friction angle. At higher confining pressures, you get a smaller angle of shearing resistance, because the three effects. You may have dilatancy, particles will move up much faster if the confining stress is less. If the stresses are very high, the particles may crush. So that is the second one. The third is because of the particle orientation. In case of fine-grained soil, the finer particles, they're trying to become more parallel or less parallel depending on that. So in some soils, you find that the curvature is very important and the failure envelope is not a straight line. So this is the principle of direct shear test I was mentioning to you. You have one lower box, another, apply the normal force, apply shear force. You are shearing along a predetermined failure plane. And so if I look at the sigma versus tau, when you apply the normal force, you are increasing, stress path is to the right. When you apply the shear force, stress path is to vertically up. The problem with direct shear test is the stress distribution is not uniform. As the box moves around, you can see that the soil here is not in direct contact. This soil is resting on the lower box. Similarly, you find that the box is resting on part of the soil. So you find that the stresses are highly non-uniform. The area of contact from here to here is changing. Originally, when the box was here, you had the full contact. If you look at it from here to here, but once it moves, the contact is less. The advantages are it's very easy to perform, it is very inexpensive, and a lot of experience is there. Even a technician can carry out, an engineer doesn't have to do that. But the disadvantage is it's a very small box, hardly 6 centimeters by 6 centimeters. The specimen size is very small, and the displacement also you can't go for more than maybe 2 millimeters or 1 millimeter. And you are forcing failure along a given surface, whereas the real failure may be some other plane.